In this video, we're going to talk about Dalton's law of partial pressures. Say you have a sample containing a mixture of ideal gases. The pressure exerted by each gas, we'll call this the partial pressure for the gas, is independent of the other components. Therefore, the total pressure of the sample will be the sum of the partial pressures. Let's give an example. Imagine I have three gases, gas A, gas B, and gas C, and I put all of these gases into a container. Each of these gases independently exerts some pressure on the walls of the container, and we call the pressure contributed by a specific gas the partial pressure for that gas. Each gas in the container will have a partial pressure. If we add up all of these partial pressures, we'll get the total pressure. Hence, total pressure is just the sum of the partial pressures of all of the gases in the container. This phenomenon is referred to as Dalton's law of partial pressures, and it can be expressed with this equation, where P total is the total pressure of all the gases in the container, and P1, P2, P3, etc., those are the partial pressures of the individual gases that make up the mixture. You'll be asked to use this on problems, and it's usually never as simple as just plugging things into a formula. Be prepared to combine the law of partial pressures with the ideal gas law. Let's look at an example. When 6.0 liters of helium gas and 10.0 liters of nitrogen gas, both at 1 atmosphere, are pumped into an evacuated 4.0 liter rigid container, evacuated means all the gas has been sucked out. At 0 degrees Celsius, what is the final pressure in the container at 0 degrees Celsius? Each of these two gases, nitrogen and helium, is being transferred from one tank into the other final tank. The starting pressure for each is 1 atmosphere. We can anticipate the ending pressure for each gas is going to be higher because both gases are being squeezed into a smaller container. We need to find the partial pressures of the gas, and then we need to add the partial pressures to get the final pressure in the tank. There's one other piece of information in here that is useful. We're starting at 0 degrees Celsius and we're ending at 0 degrees Celsius. Hence, our temperature stays constant. That will be important in a minute. So let's wrap our head around this. We're going to start with 6 liters of helium gas and 10 liters of nitrogen gas, and we're going to be squeezing both of them into a 4-liter container. We will take our ideal gas law. We notice that N, T, and R will remain constant, and that the only thing that's changing is the volume and the pressure. We can use algebra to rearrange PV equals nRT to get Boyle's law. P1V1 equals P2V2. Now we're going to use this equation on each gas separately. P1 is going to be the initial pressure, which is going to be 1 atmosphere for both gases, and P2 is going to be the final pressure, and each gas is going to have a different final pressure. That's actually going to be the partial pressure of that gas in the container. If we rearrange this equation, we get P2 equals V1 over V2, initial over final volume, times 1 atmosphere. And we are going to plug in our numbers for both of these gases. And we notice that the partial pressure for the helium is going to be 1.5 atmospheres, and the partial pressure for our nitrogen is going to be 2.5 atmospheres. If we add up our partial pressures of helium and of nitrogen, we're going to get the total pressure, and that's what we want. Here's a diagram of what this would look like, where we have all of our gases in the final container, and each of them exerts a certain amount of pressure in the container. Our P total will be 1.5 atmospheres plus 2.5 atmospheres, and that will give us 4.0 atmospheres of pressure in the container once both of the gases have been combined. Now let's move on to another way to determine partial pressure. We're going to be using the mole fraction, which is denoted by the Greek letter chi. That's not an X, that's a chi. And the mole fraction is just the moles of the specific gas you're looking at divided by the total moles of gas in the container. We can determine the partial pressure for a gas, like gas A, by multiplying the mole fraction for that gas by the total pressure in the container. Let's try to reason this out. I want you to recall that when we're talking about gas pressures, the identity of the gas particles doesn't matter. I could put 10 moles of oxygen gas in this container, and it would have the same pressure as 10 moles of nitrogen gas would, and that would have the same pressure as 10 moles of sparkly rainbow unicorn gas would, assuming we are at constant temperature. Now say I have 10 moles of a mixed gas in the container. 5 moles are nitrogen, 3 moles are oxygen, and 2 moles are sparkly rainbow unicorn gas. If I want to know the partial pressure of sparkly rainbow unicorn gas, all I need to know is the total pressure and the mole fraction. So let's say the total pressure in our tank is 1 atmosphere. To get the partial pressure of our sparkly rainbow unicorn gas, we just need to multiply the total pressure in our tank, which is 1 atmosphere, by our mole fraction, which is 2/10, and we get 0.2 atmospheres. We could do the same thing for nitrogen and oxygen. Using the same formula, we get 0.5 atmospheres for nitrogen and 0.3 atmospheres for oxygen. All of these partial pressures add up to 1.0 atm, which equals the total pressure in the tank. So what this mole ratio equation is really doing for us is helping us figure out the fraction of the total pressure that is attributable to the particular gas we're looking at it, and that fraction is the partial pressure. Here's another example. A mixture of hydrogen gas and oxygen gas exerts a total pressure of 1.5 atmospheres on the walls of its container. If the partial pressure of hydrogen is 1 atmosphere, find the mole fraction of oxygen in the mixture. This is a kind of complicated multi-step problem, so let's break it down. We have been given the total pressure as well as the partial pressure of the hydrogen. We need to find the mole fraction of the oxygen. So let's come up with a strategy. We know that we're eventually going to have to use this equation here to find the mole fraction. However, in order to get here, we're going to need to know the partial pressure of our oxygen. We can do this by using Dalton's law of partial pressures. We rearrange our equation, and we get the partial pressure of oxygen equals the total pressure minus the partial pressure of hydrogen. When we plug our numbers in, we find that the partial pressure of oxygen is 0.5 atmospheres. So far, so good. Now we have to take the information we have and we have to apply it to that partial pressure equation that uses mole fractions. Here's what we've been given. We are going to take this equation and we are going to rearrange it to solve for the mole fraction of oxygen. Once we have it rearranged, it's just a matter of substituting in our numbers, and we get a mole fraction of 0.33. Now let's talk about a technique called collecting gas over water. Say you have a chemical reaction where one of the products is a gas, and you want to find out how much gas you have. Maybe you need to know the mass or the moles or the percent yield or whatever. But you need to know how much gas you have. This is not easy, but it is feasible if you use a procedure called collecting gas over water. Here's how it works. A vessel, such as a test tube or a beaker or a graduated cylinder that has been filled to the brim with water, is inverted. That means turned upside down in a tank of water. The gas from the chemical reaction is bubbled into it, usually through a tube. as the gas gets bubbled in, it pushes water out of that vessel. And this allows for the gas to be measured, and it also minimizes the amount of air that would contaminate the sample if we measured it in other ways. The pressure inside the tube is the same as the atmospheric pressure is. That's because the gas inside the vessel is pushing against the water, which is pushing against the atmosphere. The total pressure inside the vessel equals atmospheric pressure. Here's where you have to be careful. The total pressure inside the vessel is not just the pressure from the gas made during the reaction. It's not pure. It's also mixed with water vapor. How much water vapor is in the vessel depends on the temperature. The higher the temperature, the higher the vapor pressure of the water, and the more water vapor will be in that gas sample. In order to find the partial pressure of the gas you're collecting, it's going to take a few steps. First, check the current atmospheric pressure using a barometer. Then, measure the temperature and look up the partial pressure of water vapor at that temperature from a table. Once you've done this, you can use Dalton's law of partial pressures to figure out the partial pressure of the gas that was produced by the chemical reaction. You're going to do this by subtracting the partial pressure of the water vapor from the total. Your result is going to be the partial pressure of the dry gas. That's what we call it, the dry gas. Once we know the partial pressure of the dry gas, we can do all sorts of things with it. Here's an example. A 0.219 gram sample of an unknown gas was collected over water at 25 degrees Celsius and 1.01 atmospheres. The collection cylinder contained 35.45 milliliters of gas after the sample was released. The vapor pressure of water at 25 degrees Celsius is 3.126 times 10 to the negative 2 atmospheres at 25 degrees Celsius. Find the molar mass of the unknown gas. Okay, this is a lot. Let's break the problem down. We know that we have 0.129 grams of our gas. They also told us what the total pressure in the collection cylinder is. That's 1.01 atmospheres. We know the volume of gas is 37.45 milliliters. Okay, let's think about this for just a minute. We have a cylinder with 37.45 milliliters of gas. That is a mixture of the gas from our chemical reaction and water vapor. And the pressure inside is 1.01 atmospheres. Okay, let's move on. The partial pressure of water at 25 degrees Celsius is 3.126 times 10 to the negative 2. And they've told us what our temperature is. Since we are dealing with gases, we must translate our temperature from Celsius into Kelvin, or we might run into some problems. We want to find the molar mass of the gas. Here's our strategy. The first thing we're going to do is find the partial pressure of the gas. And we'll be able to do this using Dalton's law of partial pressures. Once we have this, we can use PV equals nRT to find the number of moles of the gas we produced. And since we know the mass of the gas we produced, we can divide that by the number of moles to get our molar mass. Okay, let's go ahead and do this. Here is Dalton's law of partial pressures. We're going to rearrange this equation because we want to know the partial pressure of the gas from the reaction. We know the total and we know the partial pressure of the water vapor, so it's just a matter of subtracting the two. The partial pressure contributed by our reaction gas is 0.98 atmospheres. Now that we've done that, we are going to use the ideal gas law. I am going to rearrange it so that I can solve for n, the number of moles. And I can just plug my numbers in and solve, and I have 0.0015 moles. Now, to find our molar mass, all we have to do is divide our mass by the number of moles, 0.129 grams divided by 0.0015 moles, and we get 86 grams per mole. In summary, you should now know about Dalton's law of partial pressures, and you should be able to find the total pressure of a mixture of gases by adding the partial pressures of the gases that make up that mixture. You should also know about the mole fraction, which is the number of moles of a particular gas divided by the total number of moles of gas in the container. If we know the mole fraction of a particular gas and the total pressure in the tank, we can find the partial pressure for the gas by using this equation.